Okay, so this is an example of what we call an Atwood machine. Now, this Atwood machine is basically just a pulley, and it has two masses strung around it, so that one is on one end and one is on the other. Now, in the initial idealized version that we're going to be working with, we have the following conditions. We have a massless pulley. We have a frictionless pulley, and we have a massless string. And these are all to make our calculations much simpler. Now, in this consideration, we have the following. Our first problem is going to deal with the following situation. We have one mass, M2, that is more massive. We don't know how much more massive. And the reason we know this is because we have some acceleration. We have some acceleration in that direction. So our acceleration is in that direction, and we'll call that acceleration A. Now notice there is nothing that says that one can't be higher than the other, or they can't be on the same level, even if they're still these two masses. But to start out, when we're and that's just because gravity is going to pull them the same in this case, effectively the same amount regardless of where the acceleration due to gravity is the same regardless of position in this type of example. Now, the first thing that we should do when considering a problem like this is we should make a free body diagram for each mass. So make one for mass 1 and one for mass 2. Great. So now I'm just labeling these so that it's clear which one is which. And our only forces here are vertical. So starting out, I'm going to have a vector pulling up from the string on mass 1. And I'm going to copy that and paste it. I'm going to move it here for mass 2. Now why would the tensions from the string, these are tensions, why would those two tensions be the same? Well, if the M2 moves down, the M1 moves up in the same amount. So if M2 moves down, M1 moves up the same amount. M1 moves down, M2 moves up the same amount. And they have the same amount of time it takes for them to do that. So if we consider the displacement over time and the velocity over time, it's as if they're connected. One moves, the other moves. So the tension of the string is going to be uniform. Their acceleration between each of them should be the same. It's simply the so let's have a look at this. We have mass 1 pulling down some amount. It's going to be less than the tension. And that's because the net force on both of these objects should equal their mass times their acceleration. Then we pull down on M2 a little more so that it's slightly larger than tension. If we have a net force downwards, then that will be an indication that the object should be moving downwards, and likewise, if we have a net force upwards for m1, that'll be an indication that it will be moving upwards. So if I have the same tension across each of these, well, the tension here, tension in this string, is going to be greater than, or is going to be less than the force of gravity due to the mass. So it's not going to be pulling that mass up, the mass is actually going to be falling because the net force is in the downward direction. Likewise, if mass 1 has a lower mass than the lower force on it than the value of tension up, which is the case here, it will be moving up this way, because the tension is stronger than the force of gravity down on it. So this is also a classic example of what happens with pulleys redirecting forces. M1 moves up, M2 moves down, but the force ends up being just redirected. The force from 1 is redirected. Let's look at what we have here in terms of equations. So we don't know the tension quite yet. We'll be able to find that, but we also know that we have the force of gravity on M1 is equal to M1g and we know that the force of gravity on M2 is M2g. So now what we say is, okay, well, based on Newton's laws, his first law says that we have no change in motion if there are no unbalanced forces. Well, that doesn't stand here because we have unbalanced forces. We have an acceleration. So we really should just be looking at the second law, which is a generalization of which the first law is a special case. So Newton's second law says that the sum of the forces, this is my quick summation notation, of any system should tell us the mass times the acceleration. Well, we can specify this to the situation at hand. We can say that the sum of the forces on M1 is equal to M1A which we also, M1 times A, but we also know that that's equal to the force of gravity going down subtracted from the tension going up. So we have the tension, which is the larger force, affected by the force of gravity, or countering the force of gravity, M1g, and the net force is just the tension pulling down on M1, or pulling up on M1, subtracting the force of gravity pulling down on M1. As we can see here, the net vector is going to be upwards and smaller than either of these, just based on their relative magnitudes. Likewise, we can look at M2. The sum of the forces on M2 is equal to M2A, which is equal to the force of gravity down on M2 subtracting the tension up, because it's falling down, so we want the bigger force to be in front here. So M2g minus tension. Now, if I'm running through this, I can say, okay, well, this looks like a system of equations. If the tension is the same, I can probably eliminate it and solve for what I'm looking for, which initially I'm going to say I want to know what the acceleration is. So I want to know two things. What is tension? What is acceleration? So now I have a system. Let me solve it by by adding these two equations. So if I were to add these two equations, I'd get the following result. Obviously not lorem ipsum. I'd get on the left side, well, m1a plus m2a is just m1a plus m2a. And that's equal to, on the right side, well, plus tension minus tension is 0. And m1g negative plus m2g positive is just m2g minus m1g. So this equation is combining these two other equations in my system, and we're going to isolate A to solve. So if I isolate A, I get A times m1 plus m2 is equal to G times m2 minus m1. And then I can solve that to say A equals G times m2 minus m1 over m1 plus m2. So that's a pretty standard equation. I'm going to actually do this. And make a line there just to make it look pretty. Okay, so this result right here is my acceleration equation for a standard Atwood machine, basic, very simple Atwood machine. Likewise, I can take this and plug it back into my original equation to find the tension. So let's give some values here. I have a general solution, so let's give some values. M2 is equal to 2 kilograms. M1 is equal to 1 kilogram. And we'll say that G is 10 meters per second squared down. So if I solve this equation, what I find is that I get A equals, as a value, 10 times 2 minus 1, plugging into my equation over here, divided by 2 plus 1, which is equal to 10 times 1, which is 10, over 3, which is equal to 4/3, which is pretty small. So I have 10 times 2 minus 1 over 2 plus 1. Okay, so and if I were to look at this in terms of that is not correct. Wow. That is 3 1/3, which is 1/3 of gravity. So check your math always. Don't simplify 10 thirds down to 4 thirds. That doesn't make any sense. So we have a final acceleration of 3.33 meters per second squared. Here it's going up, here it's going down. Now, what I can do is I can take that 3 1/3 value and plug it into this equation here, let's say, to find the tension. So if I copy this and I paste it, I can see that I'm going to end up getting, if I isolate the tension, I end up getting tension is equal to m1a minus m1g plus m1g, which is equal to just m1 times a plus g, which is equal to 1 times 3.33 plus really 10 thirds plus 10 which is equal to about 4 thirds. No, it's 4 thirds gravity, which is 13.33. It's 4 thirds g if you use the g value. If you actually substitute in 10 or 9.1, it's going to be a slight, you're going to get a numerical value. So this tells me 4 thirds times g m1g, really. So 13.33 newtons of tension in this case. So that 13.33 newtons goes up this way, and it goes down this way, and we have a tension value and we have an acceleration value for this system. Now, if we have the equations here, as long as you don't make the same mathematical mistakes I did, you will get a value for any situation if you just plug in numbers. So it's beneficial to find the equation first, and then to find the numerical answer after the fact. So this is a simple acceleration problem. Obviously, if the acceleration is 0, then I have 0 on one side of this equation. I have m2g minus m1g on the other side. So I find that m2g and m1g are the same, and therefore the masses are the same. And you can just calculate that that value out. You can also calculate that the tension is equal to m1g, and the tension is also equal to m2g. Okay, so that is the end of this Atwood machine problem. Hopefully it's helpful.